Hello friends, in the previous lecture we discussed the isentropic relations for a process in case of pure substances. Then we learned that heat is in essence a form of disorganized energy and some disorganization, that is entropy, flows with heat. The second law requires that the increase in entropy of the cold body be greater than the decrease in entropy of the hot body, and thus the net entropy of the combined system increases. In today's discussion, we shall be dealing with isentropic efficiencies of steady flow devices, entropy balance, and mechanisms of entropy transfer. Isentropic efficiencies of steady flow devices. We know that irreversibilities inherently accompany all actual processes and that their effect is always to downgrade the performance of devices. In engineering analysis, it would be very desirable to have some parameters that would enable us to quantify the degree of degradation of energy in these devices. In the earlier lectures, we analyzed the cyclic devices such as heat engines and refrigerators. Now we extend the analysis to discrete engineering devices working under steady flow conditions such as turbines, compressors and nozzles, and we examine the degree of degradation of energy in these devices as a result of irreversibilities. However, first we need to define an ideal process that serves as a model for the actual processes. Although some heat transfer between these devices and the surrounding medium is unavoidable, many steady flow devices are intended to operate under adiabatic conditions. Therefore, the model process for these devices should be an adiabatic one. Furthermore, an ideal process should involve no irreversibilities, since the effect of irreversibilities is always to downgrade the performance of engineering devices. Thus, the ideal process that can serve as a suitable model for adiabatic steady flow devices is the isentropic process. The more closely the actual processes approximates the idealized isentropic process, the better the device performs. Thus, it would be desirable to have a parameter that expresses quantitatively how efficiently an actual device approximates an idealized one. This parameter is the isentropic or adiabatic efficiency, which is a measure of the deviation of actual processes from the corresponding idealized ones. Isentropic efficiencies are defined differently for different devices, since each device is set up to perform different tasks. Isentropic efficiency of turbines. For a turbine under steady operation, the inlet state of the working fluid and the exhaust pressure are fixed. Therefore, the ideal process for an adiabatic turbine is an isentropic process between the inlet state and the exhaust pressure. The desired output of a turbine is the work produced, and the isentropic efficiency of a turbine is defined as the ratio of the actual work output of the turbine to the work output that would be achieved if the process between the inlet state and the exit pressure were isentropic, that is, eta T is equal to actual turbine work divided by isentropic turbine work and is equal to W A upon W S. Usually, the changes in kinetic and potential energies associated with a fluid stream flowing through a turbine are small relative to the change in enthalpy and can be neglected. Then, the work output of an adiabatic turbine simply becomes the change in enthalpy, and the above equation becomes eta T is equal to H1 minus H2A divided by H1 minus H2S. Here H2A and H2S are the enthalpy values at the exit state for actual and isentropic processes respectively. The value of eta T greatly depends on the design of the individual components that make up the turbine. Well designed large turbines have isentropic efficiencies above 90%. For small turbines, however, it may drop even below 70%. The value of the isentropic efficiency of a turbine is determined by measuring the actual work output of the turbine and by calculating the isentropic work output for the measured inlet conditions and the exit pressure. This value can be used conveniently in the design of power plants. Isentropic efficiencies of compressors and pumps. The isentropic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work input, that is, eta C is equal to isentropic compressor work divided by actual compressor work and is equal to Ws upon Wa. Notice that the isentropic compressor efficiency is defined with the isentropic work input in the numerator instead of the denominator. This is because Ws is a small quantity than Wa, and this definition prevents eta C from becoming greater than 100%, which would falsely imply that the actual compressors performed better than the isentropic ones. When the changes in kinetic and potential energies of the gas being compressed are negligible, the work input to an adiabatic compressor becomes equal to the change in enthalpy, and the above equation for this case becomes eta C is equal to H2S minus H1 divided by H2A minus H1. Here H2A and H2S are the enthalpy values at the exit state for actual and isentropic compression processes respectively, as illustrated in this figure. Again, the value of eta C greatly depends on the design of the compressor. Well designed compressors have isentropic efficiencies that range from 80 to 90%. When the changes in potential and kinetic energies of a liquid are negligible, the isentropic efficiency of a pump is defined similarly as eta C is equal to Ws upon Wa and is equal to V into P2 minus P1 divided by H2A minus H1. When no attempt is made to cool the gas as it is compressed, the actual compression process is nearly adiabatic, and the reversible adiabatic, that is isentropic process, serves well as the ideal process. However, sometimes compressors are cooled intentionally by utilizing fins or water jackets placed around the casting to reduce the work input requirements. In this case, the isentropic process is not suitable as a model process, since the device is no longer adiabatic and the isentropic compressor efficiency defined is meaningless. A realistic model process for compressors that are intentionally cooled during the compression process is the reversible isothermal process. Then we can conveniently define an isothermal efficiency for such cases by comparing the actual process to a reversible isothermal one as eta C is equal to Wt upon Wa. Here Wt and Wa are the required work inputs to the compressor for the reversible isothermal and actual cases respectively. Isentropic efficiency of nozzles. Nozzles are essentially adiabatic devices and are used to accelerate a fluid. Therefore, the isentropic process serves as a suitable model for nozzles. The isentropic efficiency of a nozzle is defined as the ratio of the actual kinetic energy of the fluid at the nozzle exit to the kinetic energy value at the exit of an isentropic nozzle for the same inlet state and exit pressure. That is, eta n is equal to actual kinetic energy at nozzle exit divided by isentropic kinetic energy at nozzle exit, and is equal to V square 2A divided by V square 2S. Note that the exit pressure is the same for both the actual and the isentropic processes, but the exit state is different. Nozzles involve no work interactions, and the fluid experiences little or no change in its potential energy as it flows through the device. If, in addition, the inlet velocity of the fluid is small relative to the exit velocity, the energy balance for this steady flow device reduces to H1 is equal to H2A plus V square 2A divided by 2. Then the isentropic efficiency of the nozzle can be expressed in terms of enthalpies as eta n is approximately equal to H1 minus H2A divided by H1 minus H2S. Here H2A and H2S are enthalpy values at the nozzle exit for the actual and isentropic processes respectively. Isentropic efficiencies of nozzles are typically above 90% and nozzle efficiencies above 95% are not uncommon. Entropy balance. The property entropy is a measure of molecular disorder or randomness of a system, and the second law of thermodynamics states that entropy can be created but it cannot be destroyed. Therefore, the entropy change of a system during a process is greater than the entropy transfer by an amount equal to the entropy generated during the process within the system, and the increase of entropy principle for any system is expressed as total entropy entering minus total entropy leaving plus total entropy generated is equal to change in the total entropy of the system, or S in minus S out plus S generated is equal to delta S system. This relation is often referred to as the entropy balance and is applicable to any system undergoing any process. The entropy balance relation can be stated as the entropy change of a system during a process is equal to the net entropy transfer through the system boundary and the entropy generated within the system. Entropy change of a system. Despite the reputation of entropy as being vague and abstract and the intimidation associated with it, entropy balance is actually easier to deal with than energy balance, since unlike energy, entropy does not exist in various forms. Therefore, the determination of entropy change of a system during a process involves evaluating entropy of the system at the beginning and at the end of the process and taking their difference, that is, entropy change is equal to entropy at final state minus entropy at initial state, or delta S system is equal to S final minus S initial and is equal to S2 minus S1. Note that entropy is a property and the value of a property does not change unless the state of the system changes. Therefore, the entropy change of a system is 0 if the state of the system does not change during the process. For example, the entropy change of a steady flow devices such as nozzles, compressors, turbines, pumps and heat exchangers is 0 during steady operation. When the properties of the system are not uniform, the entropy of the system can be determined by S system is equal to integral of S delta m and is equal to integral of S rho dV from V. Here V is the volume of the system and rho is the density. Mechanisms of entropy transfer. Entropy can be transferred to or from a system by two mechanisms: heat transfer and mass flow. Entropy transfer is recognized at the system boundary as it crosses the boundary, and it represents the entropy gained or lost by a system during a process. The only form of entropy interaction associated with a fixed mass or closed system is heat transfer, and thus the entropy transfer for an adiabatic closed system is 0. Heat transfer. Heat is in a sense a form of disorganized energy, and some disorganization will flow with heat. Heat transfer to a system increases the entropy of that system and thus the level of molecular disorder or randomness, and heat transfer from a system decreases it. In fact, heat rejection is the only way the entropy of a fixed mass can be decreased. The ratio of the heat transfer Q at a location to the absolute temperature T at that location is called the entropy flow or entropy transfer and is expressed as S heat is equal to Q upon T. Here T is a constant. The quantity Q upon T represents the entropy transfer accompanied by heat transfer, and the direction of entropy transfer is the same as the direction of heat transfer, since thermodynamic temperature T is always a positive quantity. When the temperature T is not constant, the entropy transfer during a process can be determined by integration as S heat is equal to integral of delta Q upon T from 1 to 2 and is approximately equal to summation of Qk upon Tk. Here Qk is the heat transfer through the boundary at temperature Qk at location k. When two systems are in contact, the entropy transfer from the warmer system is equal to the entropy transfer into the cooler one at the point of contact. That is, no entropy can be created or destroyed at the boundary, since the boundary has no thickness and occupies no volume. Note that work is entropy free and no entropy is transferred by work. Energy is transferred by both heat and work, whereas entropy is transferred only by heat, that is, S work is equal to 0. The first law of thermodynamics makes no distinction between heat transfer and work. It considers them equals. The distinction between heat transfer and work is brought out by the second law. An energy interaction that is accompanied by entropy transfer is heat transfer, and energy interaction that is not accompanied by entropy transfer is work. That is, no entropy is exchanged during a work interaction between a system and its surroundings. Thus, only energy is exchanged during work interaction, whereas both energy and entropy are exchanged during heat transfer. Mass flow. Mass contains entropy as well as energy, and the entropy and energy contents of a system are proportional to the mass. Both entropy and energy are carried into or out of a system by streams of matter, and the rates of entropy and energy transport into or out of the system are proportional to the mass flow rate. Closed systems do not involve any mass flow and thus an entropy transfer by mass. When a mass in the amount of m enters or leaves a system, entropy in the amount of ms accompanies it. Here S is the specific entropy, entropy per unit mass entering or leaving. So, S mass is equal to m into S. Therefore, the entropy of a system increases by ms when mass in the amount of m enters and decreases by the same amount when the same amount of mass at the same state leaves the system. When the properties of the mass change during the process, the entropy transfer by mass flow can be determined by the integration from S mass is equal to integral S delta m. So friends, here we come to the end of our discussion in today's lecture, and therefore we sum up. The work done during a steady flow process is proportional to the specific volume. Therefore, we should be kept as small as possible during a compression process to minimize the work input, and as large as possible during an expansion process to maximize the work output. Most steady flow devices operate under adiabatic conditions, and the ideal process for these devices is the isentropic process. The parameter that describes how efficiently a device approximates a corresponding isentropic device is called isentropic or adiabatic efficiency. So that is it for today. In the next lecture, we shall be discussing more about thermodynamics. Thank you very much.